The planet Neptune was discovered by a scientist who had never seen it. How on earth is that possible? This is the discovery of Neptune. In 1846, a French scientist wrote a letter to an astronomer in Berlin, saying that he had discovered a new planet, but that he needed help. You see, the scientist had never seen this planet because he didn't have access to a telescope, and it was too faint to see by eye. He included in his letter the exact coordinates of the planet's location. The very same night that he received this letter, the astronomer pointed his telescope at those coordinates and became the first person in history to see Neptune. This is a story of scientific thinking, of paying close attention to careful measurements, and above all, relentlessly pursuing the best explanations for how the universe works. So let's return to the night of the discovery. What did they actually see that night? The astronomer Gala, who received the letter, was assisted that night by an assistant named D'Arrest. This is the night sky above Berlin, September 23rd, 1846. This is the view they would have seen through their telescope. The French scientist's name was Leverrier. He calculated the position of the new planet and predicted that it should be here, which, as you can see, is disappointingly empty. Gala decided to see if the planet might be nearby anyway, so he started to read off the positions of the stars. This is the actual star chart that they used that night. I'll make this easier for us by superimposing the star chart that they actually used and the night sky that evening. When he read off the coordinates of this star, the assistant famously shouted, "That star is not on the map." Can you imagine realizing that you just discovered a new planet of the solar system? That you were the first person to see it? Let's build some intuition around what's happened so far. First things first, the prediction wasn't exactly right. So how close was it? I'm holding the smallest coin that the US makes, a 10-cent coin called a dime. If you were to take this coin and hold it at arm's length, cover one eye, and point it toward the location of the new planet, this coin would comfortably cover both the planet and the prediction at the same time. Let's review some background to make sure that we're building on a shared understanding. This is a portion of the night sky visible from the northern hemisphere. Many civilizations have connected the stars into constellations. Additionally, there are a few points of light, just a handful, that move. In fact, they appear to wander around the sky. This is where the name planet comes from. These planets have been known and tracked and worried about for thousands of years. Let's do a quick roll call. Starting with the Sun, we next have our familiar planets, Mercury, Venus, Earth, whose average distance from the Sun, about 93 million miles, or 150 million kilometers, we give the special unit 1 astronomical unit, or AU for short. I'll be using this for the remaining orbital distances. Moving on, we have Mars, Jupiter, and Saturn. These planets had all been known since antiquity. I'm showing here the night sky as seen over Bath, England on March 13th, 1781. What astronomer William Herschel saw over several days, completely by accident, was a new point of light that was moving against the celestial sphere. It took a couple of months to realize that it was a new planet, that they eventually gave the name Uranus. Before Uranus, Saturn was the farthest known planet from the Sun at roughly 10 AU, or 10 times the distance from the Earth to the Sun. Uranus doubles the size of the known solar system and comes in at roughly 20 AU. When astronomers fit the orbit of Uranus, the predicted location of Uranus in the sky and the observed locations started to diverge. Why did this happen? The answer is Neptune actually exists and exerts a gravitational pull on Uranus. So if your model of the solar system doesn't include Neptune, you will calculate the wrong orbit for Uranus. An astronomer published tables in 1821 of the locations of the planets for years to come. By the mid-1840s, Uranus's predicted location was off by around 2 arc minutes. We were previously using a dime held at arm's length against the sky. The diameter of that dime covers about 1 degree of arc on the sky. When you want to get more precise than degrees, we cut 1 degree into 60 arc minutes. If you need still more precision, then further cut each arc minute into 60 arc seconds. It turns out that the height of the number 0 in the year written on the dime is about 2 arc minutes tall when held at arm's length. So what this means is, when held up against the sky, Uranus would be predicted to be on one side of the 0, and its actual position would be on the other side of the 0. That's right around the limit of what the human eye can perceive, which means, to quote from the book The Discovery of Neptune, if the real and theoretical Uranuses, 2 arc minutes apart, could have been placed side by side in the sky, they would have appeared to even the sharpest naked eye as a single planet. But of course, astronomers use telescopes, and a 2 arc minute error is unacceptable even for the instruments of the time. At the core, there's an error. This means that at least one of the following had to be wrong: the theory, the model, or the observations, and possibly more than one. Theory is where you hypothesize the rules of a game, like how the pieces are allowed to move. Model is where you set the pieces on the board. Observation is when you're checking the world and comparing it with what you predicted using theory and model. A quick recap of Newton's laws. First up, the law of universal gravitation. Every particle in the universe attracts every other particle in the universe with a force equal to big G, m1, m2, over the distance between those masses squared. Newton's laws of motion. First law, a body at rest tends to stay at rest. A body in motion tends to stay in motion in a straight line unless acted upon by a force. Second law, F equals ma, or A equals F over m. The acceleration a body experiences is directly proportional to the net force applied divided by that body's mass. Third law, for every action there is an equal and opposite reaction. Newton's laws give Leverrier the core of the theory part. The two models under consideration are the default model of known planets and an alternative model that has a planet Neptune with some calculated orbital parameters. I'll play through this simulation a few times. The top plot shows the magnitude of the force on Uranus due to Neptune. The bottom plot is the angular error that you would measure from Earth due to Neptune's influence. This final run shows the same plots as last time, but I've decomposed the top plot into a yellow and centrally directed and red tangentially directed components. Having a scientific model that makes accurate predictions is important, but it is not enough. I really like David Deutsch's approach to talking about scientific explanations, especially in his excellent book, The Beginning of Infinity. Let me contrast the geocentric Ptolemaic approach with Leverrier's, based on Newton's. Ptolemy's theory is that the celestial realm is spherical and moves as a sphere. The Earth is at the center of the cosmos, and planets move in circles or circles upon circles called epicycles. Ptolemy's model was Earth first, then the Moon, Mercury, Venus, Sun, Mars, Jupiter, Saturn. First, the discovery of Uranus was an accident, so both Ptolemy and Newton could simply add the new knowledge to their model. However, what to do with the observations of the orbit of Uranus over time? Well, Ptolemy doesn't have an explanation for the way planets move, just that they are circles upon circles. There is no reason to suggest, nor is there a mechanism that would drive you from the model to looking for a new planet. Newton's approach is entirely different. The planets move the way they do because of forces, and gravitational forces are produced by masses. As David Deutsch says, one attribute of a good explanation is that they are hard to vary. Unless you think Newton's law of gravity might not be right, perhaps the model needs to be updated. In stark contrast, the error in the solar system model suggests that there might be an explanation for this error. And when you add a massive planet to the model to fix the observed error, you are actually explaining something real about the solar system. That mass is not just an epicycle, it's actually a planet that actually exists. I want to end by revisiting the actual discovery to give a wider perspective on it. We sit on a spinning rock in a vast empty space, looking into the night sky and wondering what is out there and how it all works. We invent stories, we guess, we bluster, we create explanations, and every so often, we make discoveries. Hundreds of years ago, a scientist spent months calculating orbits based on Newton's laws, and decades worth of careful astronomical observations. I like to try to imagine what was going through his mind the last few days before he concluded with his prediction. He finished by scribbling a few markings on a couple of pages, and then he could see it in his mind. He could see it in the calculations. He could see it in the tiny irregularities in the motion of the planets. He imagined that he had found a whole new world and knew where it was. And he was right.